Hi, my name is Douglas Hill, and I've come up with a system here that I wanted to share with everyone concerning prime numbers and prime composite numbers. For a nutshell, it's actually much bigger than that. I'll just talk about that in other videos, but to grab people for now, I wanted to show prime numbers and prime composite numbers and how they are formed by a geometric progression. I show that they do have a position in time and space. They numbers themselves are not arbitrary. Uh, I will explain in further videos about how this is a doubling circuit and describes the flow of energy. Um, like I say right now, just to grab people and show you that this does work, I'm going to blow the doors off of prime numbers and prime composite numbers. Uh, Prime numbers and prime composite numbers are not random. They are, in fact, a geometric progression. I'm going to show you how they are a geometric progression. Now, this chart, I'm going to work off of this mostly because I don't have a bunch of scribbly lines to it as I plotted my points out uh, while I was discovering this. And it gets kind of messy, and I'm sure it'd be difficult to see on the video, so I'm going to describe it here using this chart. And you'll see very quickly, there's nothing too special about this, right? We have a bunch of circles. This should actually be a slow spiral coming out. We have to keep in mind that I do have a jump point here at the between the 12 and 1 o'clock position. Because it's not a spiral, that would actually be a smooth progression out. And that's going to come in important in later videos when we talk about prime quadruplets and the centers of prime quadruplets and why those are important. Suffice to say for now, I had to do it in circles. I didn't have the machine to draw the spirals out. You know, I was sitting there with a compass, so I just went with it. So I started off, I have 12 positions like on a clock, and start off the 1 o'clock position with what? Number one. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Nothing special, right? Just a standard numeric progression from 1 into infinity. But you'll notice that some of these are marked in red. What are these red numbers? These are prime numbers. These are prime numbers as stated by modern mathematics. I will prove a few different things. 3 is special. 2 doesn't seem to get involved. 1 should actually be marked in red there. And 3 has a special action that will be discussed in later videos. 1, 5, 7, 11. These are the areas that contain all prime numbers and prime composite numbers. So if we're looking at this and we see that we have our reds here, we have a strong, heavy consolidation of prime numbers in the beginning of the sequence, and I can explain that by saying we start off with multiples of 5. 5 is smaller than 7. Multiples of 7 coming out, of course, are going to be a little more, but then you have the 5s and 7s mixed. Okay, this is why it looks random until you do the geometric progression. 7 is smaller than 13. Then you have the multiples of 5, 7, 11 would be the next one. 5, 7, and 11 coming out in your sequence. Uh, this goes on into infinity. Now, if I begin, let me start with the geometry of it. If I do my multiplication tables and I do my multiples of 1 times 1 is 1 times 2, 2, 1 times 3, 3, 1 times 4, 4, right? And into infinity. And if I connect each plotted point, I get a spiral going clockwise. Now I do my multiples of 2. 2 times 1 is 2. 2 times 4, or 2 times 2, 4. 2 times 3, 6. 2 times 4, 8. 2 times 5, 10. 2 times 6, 12. I made a hexagon going clockwise. Plot my points. Get the threes. 3 times 1 is 3. 3 times 2, 6. 3 times 3, 9. 3 times 4, 12. I've made a square. The square continues out into infinity. Multiples of 4, I get a triangle. Multiples of 5, I get a 12-point star. The 12-point stars and the prime numbers are the only ones that hit in areas 1, 5, 7, and 11. And it makes this X. All prime numbers and prime composite numbers are going to show up in this X. And here's how we're going to differentiate between the two here in a moment. But let me continue with this. Makes a 12-point star. Multiples of 6. 6 times 1, 6. 6 times 2, 12. 6 times 3, 18. 6 times 4, 24. 6 times 5, 30. If this was plotted, we would have a straight line. And if they were raised, it would be pointing out into infinity both directions. Now, when I get to 7, I find that I have another 12-point star. But it goes counterclockwise when I plot it. So 5 and 7 are reciprocating action of one another. I get to 8, I have another triangle. It's reciprocating action of 4. Multiples of 9, another square, just like with 3. Multiples of 10, reciprocating action, again, clockwise hexagon as opposed to the 2, which is counterclockwise hexagon as opposed to 2, which is a clockwise hexagon. And 11 spirals counterclockwise away from the center, and 1 spirals clockwise. When I get to 12, it's the only number with no reciprocating action, and if we plot this, it is a ray shooting off into infinity one direction. Now, all these other functions, reciprocating function of each of these multiples adds 12. Reciprocating action of 1 is 11. 11 plus 1 is 12. Reciprocating action of 2 is 10. 10 plus 2 is 12. Reciprocating action of 3 is 9. Again, adds to 12. Reciprocating action of 5 is 7. Adds to 12. 6 is its own reciprocating action. 6 plus 6 is 12. This is important later. We need to understand it now because these geometries are what give prime numbers and prime composite numbers their place in space and time. I describe this to my friends as I found a way to find all prime and prime composite numbers. It's like shining a flashlight and your answers are in the shadows. Okay? So when I do my multiples 5 and 7, 5s are green, 7s are in red, and this one line across here was accidental, and I marked that in my notes over here somewhere. Anyways, as I come out with my multiples of 5 and 7, everywhere they touch in quadrants 1, 5, 7, and 11 are prime composite numbers. Okay? Everywhere that they don't touch is a prime number. Again, it's like shining a flashlight. Your answer is in the shadows. They are the negative side of the geometric progression, the underside, the side not seen. But we can see them now. Let's start with 5. 5 times 1 is 5. 5 times 2 is 10. 5 times 3 is 15. 5 times 4 is 20. 5 times 5 is 25. That's the first time, other than the 5 itself, that we hit in areas 1, 5, 7, or 11. And that is not a prime number. Well, it's a prime composite number. And this one's kind of special because when we get the square root of it, it actually gives us 5. Okay? So, without getting into it too deeply, we can shoot each one of these out in any direction. Say 1 plus 12 is 13. 13 plus 12, 25. 25 plus 12, 37. 37 plus 12, 49. 49 plus 12, 61. 61 plus 12, 73. Now, any of the numbers in the 1 o'clock position, when we begin square root of each one of these, square root of 1 is what? 1. Right? First number in our sequence. Square root of 13 comes up as a decimal, but then when we get to square root of 25, it comes up a whole number, 5. 5 is going to be first in our sequence, besides 1. 5. 3 is special. I'll get back to you about 3 in later videos. It is I believe, a torquing action, but like I say, I'll get back to that later. 121, 11. Okay, so when we get the square root of any of the numbers in column 1, we can predict what these are going to be by just simply adding 12 to each value. If it comes up a whole number, that is going to be the next